David Smith here with one more flipped classroom math video for your enjoyment. 3 tips. First, you can speed up or slow down the playback if that helps you follow along. Second, you can pause anytime to catch up with your notes or think a little harder. Lastly, you could turn on the captions, which will show you my words on the screen below. Today's lesson covers properties or rules that we can use when we manipulate integrals. So this looks like a lot of stuff on the board. I want to go through it real quick and then we'll do some examples using these rules. Now I've named them according to kind of our history going through differentiation and what the rules do. These are not official names, but I think we'll find it helpful when we do examples later and when we work on this in our class. We can call these rules by some names. So the first one, this is like a constant rule. If I have a constant times a function and I'm taking the derivative from a to b of this term here, I can pull my constant out of my integral and multiply the constant times the integral of the function. And guess what? Let's just call that the constant rule. Next one, if I have a sum or a difference of 2 functions and I'm integrating them from a to b, then I can integrate each one separately from a to b and add or subtract them. So this is just breaking this down into 2 integrals instead of 1 integral. So I'm calling that the sum difference rule. Check this next one out. If I'm integrating any function from a to a, that's just 0. And that makes sense because there's no area under this line. We're not going anywhere. We're just at one point. So if you're integrating from a to a, that's 0, and we'll call that the 0 rule. This next one, I call it the reverse rule. If I'm integrating from a to b, f of x dx, then I can switch my direction. I can integrate from b to a, and that's just negative of the integral from a to b. So I'm going to call that the reverse rule, because I'm just integrating in a reverse direction on my variables, on my boundaries. Okay, this last one looks a little more complicated, but not really once you get it. If I'm integrating from a to b, and c is in between a and b, then the integral from a to b is the same as the integral from a to c plus the integral from c to b. And we're going to do that with an example in a minute so you can see how that looks. But I call this one the interval rule. Okay, let's do some straight up problems that make use of all those rules I put on the last board. Okay, so you want to have those notes handy for doing these problems. So before we start, we've got 4 givens. So for example, the first given is 0 to 3 of f of x dx. I don't know what that function is, but we know when we take that integral over this interval, we get a result of 5. Okay, so cool. That's that definite integral. And you can see I have this one, and this one. This is another one with f of x, and then these 2 are g of x. So I'm not going to explain them all. You can see them. We know how this notation works. Again, we don't know what the functions actually are. We just know the results of the integration over a specific range or interval. Okay, first problem. The integral from 0 to 3 of 2 times f of x plus g of x. So pause the video and see if you can solve that one through. Do a plug-in step and then evaluate that to get your answer. Let's see how you did. So I can pull my 2 out. I'm going to evaluate first off. Notice how the interval is 0 to 3. And we do have some results here that go from 0 to 3. For g of x 0 to 3 and for f of x 0 to 3. So that's what's going to allow us to do what we're doing here. So I pull my 2 out. And I have 2 times f of x times the integral of f of x from 0 to 3, which is 5. So that's 2 times 5 plus, and then the integral of g of x from 0 to 3 is just right there. So it's plus negative 6. 2 times 5 is 10, minus 6 is 4. So that's our result for that one. Now, pause the video and give this one a try. Okay, let's see how you did. I broke this up. So this is an interval problem. To use the interval rule, we don't have anything for 0 to 4 for f of x. And we do have 0 to 3 and 3 to 4. So what I could do is I could break this one down from 0 to 4 to 0 to 3 f of x dx, and then 3 to 4 f of x dx. And then I have my numbers here. I have my 5 and my 2, plug those in, and I get a result of 7. Okay, try this one, see what you get. Okay, this one is slightly tricky. First off, you notice that our interval is 3 to 3. Doesn't matter what comes after that. We know that integral is going to be 0, so I put that in. And notice how this one is 4 to 3 f of x dx. We know what 3 to 4 is. So I could use the negative rule, and I get negative 2. So plus negative 2 is minus 2. So boom, the answer to that one is negative 2. 2 more problems, and then we'll do a graphical problem. So check this one out. It's the interval from 3 to 6 of g of x dx. So go ahead and pause the video, see what you get. Okay, this one's a little tricky. It's an interval rule problem, but we're not quite plugging it in the way you might otherwise think. Here's our full range, it's 0 to 6, and we can break that down between 0 to 3 and then 3 to 6. Now, we know what 0 to 6 is, so I put that there, there's the 10, and we know what 0 to 3 is, that's the minus 6. What we don't know is what the interval from 3 to 6 is. So we rearrange this equation, and I get the interval from 3 to 6 of f of x dx equals 16. Now, this one's even a bit more tricky. Give that a try. All right, here we go. So, first part is easy. I've got my constant. I can pull that out. So now I have 3 times the integral from 2 to 8 of g of x minus 2. And I've got no rules, though, for what to do when I have x minus 2 in there. So this is a big critical thinking step. If I have a function and I have an x minus 2 in a parentheses, what that means is whatever the graph of that function is, it's going to be shifted 2 units to the right. Okay? That's what it's going to do. If you have a parabola and you're looking at this x minus 2 squared, it takes a parabola and shifts it 2 to the right. So in fact, any function, when you have a minus 2 inside your parentheses, you're shifting it to the right by 2. So what that does is that changes our range. We're going to subtract 2 from each of these. And so this becomes 3 times the integral from 0 to 6 of just plain old g of x dx. So now we can do that. We know what this is. That's 10. And we have our 3 out here. So it's 3 times 10, or 30. Let's do a graphical one. Check this one out. So here's my function. This is f of x. This is a piecewise function. If we wanted to, we could take the time and write our piecewise function. It'd be 3 different pieces. This one, and that one, but we don't need to. We have our coordinate points, so we can do all the integrations we need. So I've labeled the points, boom, 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 boom. This is f of x, the whole function. So the first integral I want you to take is from 0 to 2 of f of x dx. So take a look at that function. It's a real straightforward calculation with the area for a triangle formula. Okay, triangle, 1/2 base times height. Base is 2, height is 4. 1/2 times 2 times 4 is 4. So that's the integral from 0 to 2 of f of x dx. Now, try this one. We're going integral from 2 to 4 of f of x dx. Pause the video, do that, and come back. Okay, another triangle. We've got this guy down here. I have my base is 2, and then my height is -3. Now, when you're calculating areas on the coordinate plane, you can have negative heights, and then you're going to get a negative area. Okay, it's when you're not on the coordinate plane, area is always positive, but in this context and in the rest of this chapter, indeed, we're going to have some negative areas. So check this out. 1/2 base times height is 1/2 times 2 times -3. That's going to give us an area of -3. So the integral of this function of f of x from 2 to 4 is -3. Now let's try this last one here. The integral from 0 to 8 of f of x dx. Pause the video. You're going to have to pull out just a little bit of those rules, and then you can calculate your area. Okay, I wanted to break it out for you before we take it any further. We've got 4 intervals here to use in the interval rule. We've got from 0 to 2. We've got from 2 to 4. We've got from 4 to 5. I'm doing it that way. And then we've got from 5 to 8. So go ahead and do that math. You've got 2 of these calculations already done. You've got 0 to 2 and 2 to 4 already done, but you just need to do the other two. Okay, I finished that up. I brought down my 4 for the integral from 0 to 2. I brought down my -3 from 2 to 4. Now doing the 4 to 5, I have this little triangle here with a base of 1 and a height of 2. So 1/2 times 1 times 2 is 1. I brought that down. And then finally, the area of this one is just length times width, we call it. We could call it base times height. So that's going to be 3 times 2, which gives me my 6. Add them all together, I've got 8. So the integral from 0 to 8 of this crazy piecewise function is 8. And that is the area beneath this function, this wacky piecewise function. Watch the video, take a minute and jot down any remaining questions so you can bring them to our next class. Also remember, you can watch the video again. Maybe that will deepen your understanding. If you like the video, please click like and subscribe.